Lecture 1.3, Introducing PID Control. One of the most ubiquitous types of controller is the proportional integral derivative PID controller. It has a transfer function with real constants Kp, Ki, and Kd given here. So we have our controller transfer function. There's a proportional term, that's just a gain. There's the integral term, which has an integral gain, and a 1 over s term, which is, of course, the integrator. 1 over s is the Laplace transform integrator. And finally, we have the derivative term with its constant, the Kd constant. Which has a term s, which is, of course, the Laplace transform differentiator. Great. Remember, the controller operates on the error e. So the PID controller effectively sums terms proportional to the error, its integral, and its derivative. Inspecting this in the time domain with error e of t, by taking the inverse Laplace transform of the output. So the output is, of course, of the controller is, of course, the product of the controller's input, E, and the transfer function of the controller, C. We take the inverse Laplace transform, we have a function of time, which is the time domain representation of the control effort. So we have three terms. We still have the proportional term, which has the error as a function of time being scaled, summed with two other terms. The integral term, which has the integral of the error from 0 to the current time, multiplying the integral gain. And then we have the derivative term, which has the time derivative of the error multiplying the derivative gain. So the control effort U is responsive to P, I, and D. P, the amount and direction of error, which makes it reactive or spring-like. So sometimes people will say that the proportional term acts like a spring. Okay. I, the integral term, which is the accumulation of error over time, which gives it a sort of memory effect, and it's mass-like. For the mechanical analogs, the mass is maybe the least direct. And then finally, D, the time rate of change of the error, which makes it anticipatory or damper-like. So the D term responds to how the error is changing. So if the error is suddenly increasing or decreasing, the derivative term will get large. What the integral term does is it takes into account an accumulation of error over time. So a small error over a long time is going to grow and in its integral. And that's what the integral term does. And of course, P is the amount of error. So it's giving us a direction and a magnitude that is proportional to the error itself. We can consider the three constants, Kp, Ki, and Kd, to be knobs with which we can include more or less of each term. So we could increase the proportional gain knob, we can increase the integral gain knob, or we can increase the derivative gain knob. And actually, traditionally, in the good old days with analog controllers, these would be implemented with circuits that included actual knobs. So it's not too wild to think like that. Just how a controller will affect the closed-loop response is significantly dependent on the plant dynamics. Okay, so not just the controller dynamics, but also the plant. Therefore, there is no way to make fully general statements about the impact of each of the PID terms. This is why we need the detailed analytic design tools of Chapter 6, so several chapters from now, and the intervening chapters hence. However, for some simple systems, we can make the assertions of Table 1.1. So I'm giving a lot of warnings here. Occasionally true generalities about PID controller terms. These are true sometimes, and especially for simple systems, but it's surprising how frequently there are exceptions to these rules. So proportional term is the first column, integral and derivative are the second two columns. So the proportional term is the workhorse, okay? It's the one that does most of the control effort comes from the proportional term, and in fact, some controllers just have a proportional term. So you can do just proportional feedback control, and your performance might not be great, but it does usually work okay with just a proportional term. The proportional term, as you increase it, it usually speeds up the response. And if you increase it too much, it can lead to instability. So small proportional gains are frequently stable. The feedback loop is frequently stable. But for large proportional gains, it is common to see a system become unstable at that point. Integral. The integral term improves or eliminates steady state error. Okay, so that's something we talked about in terms of the performance of the controller, the control system. The steady state error, the amount of error that's left over after the system comes to a steady state once we've changed the command. The integral term slows down the response. Okay, so this tends to slow down the response. You'll have the transient response become slower usually when we add in integral terms, or we add in more integral term. And it becomes a liability when it can't forget. So integral windup is what this is called. Remember that the integral term is the integral of the error as a function of time from time equals 0. So way back here. So the integral is all this. Now that's all well and good when you have an error that is sort of a steady state error that's hanging around. It'll grow and grow. However, what if your error dips down and is now over here? You're still stuck with all this accumulated integral, and that's this problem with the integrator not forgetting. It's called integral windup. And you'll see sometimes a system that can't forget what happened before, and like somebody who's still caught up on somebody that they used to date, they get sort of hung up on the past. So we have ways of dealing with that by taking a window instead of taking the integral from 0 to the current time. We can take a window, and then that can mitigate some of those integral windup effects. So it's one of the several nuances of PID control, is dealing with integral windup. The third term, derivative term, tends to speed up the response. It can yield jitter when measurement noise is large. So you can imagine that if you have an error signal that is very jittery, very noisy, that the derivative of this is going to wildly flip back and forth between a large negative number to a large positive number, the slope of this large negative to a large positive number. And if you are estimating the derivative based on just the current point and the previous point, which is frequently what we do in digital controls, or what is something that can be done in digital control, it's better to maybe have a little smoothing in your estimate of the derivative, maybe a few points, a little windowing on your derivative estimate, it can cause the system to wildly swing between wanting to push and pull back and forth at a rapid rate. So sometimes the derivative term, especially if you have a noisy error signal, you can get that. So it's a little bit dangerous to add in derivative, especially if you have a noisy measurement. It can lead to instability when measurement noise is large too. So if it becomes too bad, it can actually lead to an unstable response. So something to be careful of. It does speed up the response though, so we do like it. It does give us a nice way to improve, especially our transient response. So that's the derivative. There are many methods of tuning a PID controller, which is selecting the three gains, Kp, Ki, and Kd, to meet certain performance criteria. The root locus design method of Chapter 6 and the frequency response design method of Chapter 8 allow us to precisely design for specific performance criteria. However, there are times when specific performance criteria and involved analysis are not available or convenient. In these cases, hand tuning is possible via several algorithms. One such algorithm is presented in the following section. So it's called the Ziegler-Nichols tuning method. The Ziegler-Nichols tuning method for a PID controller is presented in the following algorithm. Step 1, set all the gains to 0. Step 2, increase the proportional gain, remember that's our workhorse, until a marginally stable response is observed. So this is typically a steady oscillation with a constant amplitude. If you increased that proportional gain anymore, it would start to go from a steady oscillation to an increasing amplitude oscillation. Okay, so this would be unstable. We want to, and then stable is going to be one that decreases in amplitude. We want to be right in between. We want to have one that's just staying at some nice steady oscillation amplitude. So this can be an initial condition response. It can be a step response. It can also be an impulse response. So all these responses will elicit a response that you can visually see if it's stable, unstable, or marginally stable. And we're going to try to find that nice marginal stability spot, and the sort of sweet spot in Kp. We record this ultimate gain Ku and oscillation period Tu. So the period that this oscillates at, once we've got that nice steady, marginally stable sinusoid here, we measure the period and we call that Tu, and the gain that we use to get that is called Ku, the ultimate gain. Okay, so then step 4 in the algorithm is to set the controller gains. So we set the proportional gain to 60% of the ultimate gain. So we'd back it off a little bit. Then we increase from 0, Ki and Kd, to these values that depend on Ku and Tu. And these are based on an analysis of common types of systems, and these work pretty well for getting performance that is potentially not optimal for your situation, but it usually gets a response that's stable, that responds quicker than it would if it was just a proportional gain controller, and that has minimal steady state error. So those are some nice features, and many controller designs have those as criteria. At least we will frequently want to dial in, like, specifically what do we want the transient response to look like. But in this case, we don't get to choose that, but it will give us something that's usually pretty reasonable. So let's try it out.